Hello, hello.
Hi,
How are you?
pretty good.
That's good. Yeah. Thanksgiving break now. No school tomorrow, Friday.
Yep, I'm going
Mhm.
home tomorrow morning.
Tomorrow morning. Yeah, because today too much traffic, right? You told me.
Yeah.
Yeah. How far is the drive to your home?
If there's no traffic, then 45 minutes.
I see, I see. That's good.
But it's
Mhm.
probably longer for you, huh? Because you said San Jose, right?
Yeah, San Jose. From Davis to San Jose, it's an hour and a half.
Yeah,
With
like,
no traffic.
yeah.
Right. But I'm I don't go there anymore, but I will get drive there on December 7th. So I'm gonna start driving around like 10:30 a.m. to get there at like 12 or like 11:30ish. Just to get ready, eat lunch, and then do the 118A review 12:30 to 2:30, and then the whole day after that at Davis.
Yeah, I'll be there.
Yes, yes. Excited to see you.
I know.
Mhm. Okay. So, were you able to do the reduction homework?
Yeah, but they all seem very like the same thing. I don't know if there's
Mhm.
um if there was like anything more to it that I missed. I can send a screenshot of my work right now.
Yeah, you can send it to Discord too, and I can download it off of Discord.
Okay.
Mhm.
Was there like any tricky stuff that you think like you added in there? Because I thought it was like very
No, the reduction stuff, after you get the oxidation stuff, then it should be easy. Like once you learn oxidation and you understand it, then the reduction stuff is like very easy.
okay.
Uh-huh.
Then the others.
Okay, got it, got it. Let me download, save, see here.
I think I was a bit stuck on the last one though.
And the last one, wait, let's see. Let me. Oh, did you send one and two? Or is
Yeah,
three and four sending as well?
yeah,
Okay, okay.
yeah. Because I had it in the same row.
Same row. Okay. Mm, Okay. Yes. So, um, looking at the final product, this is correct because we have an aldehyde and we are reducing that with a reducing agent, NABH4 or LiOH4, it doesn't matter for an aldehyde, to get the primary alcohol, which is good. That's correct. And the mechanism, hydrogen attacks that carbon, pops the bond onto the oxygen to get the O minus, and we bring in the third step, H2O plus, to protonate and neutralize the O minus. That's good. You got it. But when you draw out the BH4 minus, there is a negative charge on the B, on the boron right there with 4 bonds. But everything else is good.
Oh, okay,
Yeah. Right. And same thing with aluminum as well. Boron or aluminum with 4 bonds is going to be negatively charged.
okay, and okay.
Mhm. Yep. The mechanism here attack the carbonyl carbon, pop the bonds to the oxygen, get the O minus. We bring in the third step, H2O plus to protonate, which becomes this alcohol. That's good. Yeah, you got it. That's right. Uh-huh.
Okay.
Yeah. Did you also send? Wait, did I just send you these two problems
No, there
or
was the other one, but I wasn't able to answer the
Mhm.
fourth one. Just
The fourth one?
yeah, the bulky group.
Right. Bulky group. Let me see.
But I did have number three.
Number
So
three. Yeah,
was
let me see. Where is it? Oh, I see it. I see it. Okay. Yeah. Share screen. Okay. Okay. Number three. Okay. Yes. So this one right here is a carboxylic acid and we are reducing it with a strong reducing agent. Oh wait, I'm not sure my screen. What the heck? Screen start. Start. Okay. Okay, there we go. Okay, so this problem here is starting with a carboxylic acid, and we are reducing it with a strong reducing agent, LiAlH4, which whenever we see aluminum or boron with 4 bonds, it's going to be negatively charged. This hydrogen here is going to attack that. So if we're thinking about the whole mechanism, with a carboxylic acid, the mechanism won't be as straightforward as the other two. But if I look at your final answer here, yeah, so the final answer here, we won't get two alcohols, right? If we have a carboxylic acid and we reduce that carboxylic acid down, we're going to get a primary alcohol. So to predict the product quickly, just get rid of the carbonyl, get rid of the carbon double bond oxygen to get this final answer here, right? Reducing a carboxylic acid with lithium aluminum hydride will result in a primary alcohol. And here's the mechanism for that. I'm going to draw out the benzene with the carboxylic acid here, where we know that this hydrogen here of the carboxylic acid is acidic. And this H minus here, the hydride ion, can act as a nucleophile or a base. In this case, this hydrogen here is going to grab the hydrogen, making it act as a base, and give that oxygen a negative charge. Right. And then once we have this negative charge oxygen here, another equivalent of lithium aluminum hydride is going to come around and attack the carbonyl carbon, pop the bond onto the oxygen. But as this aluminum is losing the bond, it's going to have an empty p orbital, right? Because it's losing the octet row. So the O minus here is going to attack that aluminum at the same time. Right? And that's going to result in this O minus right here with this oxygen attached to this aluminum with its 3 hydrogens. And because this aluminum has 4 bonds, it's negatively charged. And we can think of this whole big group here as the good leaving group. Right, like think of it as like bromine, chlorine, iodine, something like that. And so to kick that good leaving group off, we're going to reform the carbonyl between that O minus and carbon right there. But that's going to break the octet row of this carbon right here, right? Because this carbon here already has 4 bonds. When we try to make a double bond between that carbon and oxygen, we're going to break the octet row. So to conserve the octet row, we have to kick off that good leaving group that we have right there. And then that is going to result in this aldehyde right here. But we don't stop at the aldehyde because we still have an electrophilic carbon to carbon that can be attacked by another aluminum hydride, lithium aluminum hydride. So bring in another one. And that's going to result in our O minus, which will eventually get protonated to become OH for the final product. Right. But the mechanism for the carboxylic acid, I wouldn't worry about the reduction because I didn't see it in her notes that you sent me. So I wouldn't worry about that. This mechanism here. Right. And then we bring in the second step, acid workup, where the O minus will grab the H from the H2O plus, kick out the water to give us a primary alcohol. Right.
Okay. So, in the first step, you had one of the bonds from hydrogen from like the AlH4 to attack the other hydrogen?
To attack the other hydrogen, and that's going to give us H2 gas. Right. Because this hydrogen here is attacking this hydrogen, giving us H2 gas. Because this hydrogen here is leaving the aluminum with that bond, grabbing that hydrogen away from that oxygen. And then that bond between the hydrogen being grabbed and the oxygen, those 2 electrons in that bond are going to go off onto that oxygen, giving that oxygen a negative charge.
Okay, so then that oxygen has the negative charge and the other one still stays as a
Carbonyl.
carbonyl.
Right. because we
Okay.
did not touch the carbonyl yet.
Okay. And then that negative charge, wait. Um, so when uh so when it forms H2 gas, right? The bond moves from the oxygen that used to be an OH, and it moves the bond to the carbonyl group.
So this bond right here between the oxygen and hydrogen, those two electrons are not going onto the carbonyl group. Those two electrons are going to go onto this oxygen atom over here, right? Because this oxygen atom right now that is neutral has two pairs of electrons. When we grab this H, when this hydrogen here grabs that H right there, and that bond between hydrogen and oxygen gets broken off onto that oxygen right there, that's going to give that oxygen an extra pair of electrons, right? So three pairs of electrons and one bond, negative charge. So we're not going to put this bond to make a double bond there. We're gonna put it on the oxygen minus. You can, right? You can make it double bond here, but that's gonna break the octet rule for this carbon here because it's gonna have 1, 2, 3, 4, 5 bonds. But when you do that, you're gonna get this product instead, which can still work. So you can do it this way if you want. It's gonna be the same thing. Double bond oxygen there, and when we do that, right, to conserve the octet rule, we have to pop one of the double bonds onto the oxygen, getting an O minus right there, which is the exact same thing as this right here. But just resonance structures of each other, you could say. So
Okay. So um so instead what you initially did was you grabbed the double bond and you moved it over.
what I initially did is I used this hydrogen with that bond right there to grab the hydrogen, this hydrogen here, and then the bond between that hydrogen being grabbed and that oxygen right there, that's a single bond. That single bond, two electrons, is going directly on this oxygen atom here, directly on that oxygen atom, giving that oxygen atom an extra pair of electrons.
Right, but like the next step
Oh, the
after.
next step.
Yeah.
Yes. Uh-huh. Yeah. So the next step here, the second equivalent of aluminum hydride, one of the hydrogens attacks the carbonyl carbon, popping the double bond onto the oxygen to conserve the octet rule. But as that happens, the aluminum is losing two electrons, right? So it's not going to have the octet rule anymore. So then this O minus here sees that. So the O minus is going to donate one of its pairs of electrons onto the aluminum. So there's two things that's happening here. Actually three things if you count the double bond popping onto the oxygen. So the first thing you could think of is that this H of the aluminum hydride is attacking that carbonyl carbon, which would pop the double bond onto the oxygen. But as that happens, this aluminum here is losing electrons, becoming more electrophilic, more positive charge. The O minus here on the other side senses that and attacks that aluminum right away.
So in this case, this like the aluminum would be or is this another floating aluminum?
Yeah, this is another, or this is a floating aluminum hydride, ALAH4, LOH4, like aluminum hydride.
But
Right.
that would be like a different one compared to the very
Yeah,
first we had.
that would be a different one than the very first one we had, because if we look at the very first one we had, as that hydrogen is being uh like as this hydrogen is attacking that hydrogen right there, we're gonna form ALH3, right? Which is neutral aluminum, because aluminum with three bonds, which you could draw out like this, is going to be neutral, right? And this neutral aluminum here is no longer nucleophilic. These hydrogens here on the aluminum can no longer attack anything because it's happy with this neutral state right now. So that's why we had to bring in a second equivalent of aluminum hydride to get these angry hydride ions because of the negative charge on the aluminum here to attack the carbon to carbon. So this right here is a second equivalent of the aluminum hydride. It's not the same one that we used in the beginning. We're bringing in another version, another mole, another equivalent of the aluminum hydride.
But since we said that ALH3 would be stable, but then that hydrogen bond goes to like backside attack the carbonyl, how
Mm-hmm.
how is it that it's how are we saying that it's like it needs
Yeah, so this one here, the one that I was talking about that's stable, is not this. That's different. These are different things. Right. The one that is stable right here is not going to attack the carbon to carbon, because if it's stable, it is less reactive. Right. If it's less reactive, it's not going to react with anything. But this one right here is unstable. The aluminum with 4 hydrogens is unstable because we have that negative charge there on the aluminum. And if something is unstable, it's more reactive. And these hydrogens here are reactive, meaning that those hydrogens there have negative charges, hydride ions. And if we see negative charge, that means that those hydrogens are nucleophiles. And these nucleophiles here are going to attack the partial positive charge carbon to carbon right there, electrophile.
okay, which is why you're saying like at the same time it is happening. So it sees the aluminum for how it is, the negative.
Right. This is the electrophile here. This aluminum here has empty p orbital because it's missing 2 electrons. So at the same time, the O minus attacks that aluminum that is missing 2 electrons.
Okay.
Right.
That makes sense. Thank you.
Yeah, no problem. Yeah. So now, do you get the rest of the mechanism here? Like once we get to that good leaving group, we get to the aldehyde, and then we do the whole like regular mechanism for aldehyde to get the primary alcohol here.
Is it just the fact that we're like adding more aluminum
hydride, right?
aluminum hydrides until get a alcohol?
Yeah. We're adding more aluminum hydride to get an alcohol, like O minus, and then the O minus will eventually become an alcohol when we bring in the acid workup step. That's right.
Okay, I think that makes sense then.
Yeah, that's good. But does this step make sense on how we got to the aldehyde from like this negative charge reforming the carbonyl, carbon double bond oxygen, kicking out that good leaving group to get to the aldehyde? Does this step make sense?
I think so. It's just repeating the same thing, right?
Oh, this one here is a new step. Yeah, this one we haven't done before. This one here is going to use one of the oxygen's pairs of electrons to go down to make a double bond between that carbon and oxygen. But that's going to break the octet rule because that carbon is going to have 5 bonds. So we're going to kick out this whole group right here as a leaving group to get to this aldehyde here. So this step here is new. This is the only step that happens, that we do that.
Okay, I think that makes sense then.
Right. Because this oxygen, aluminum, like H3 is all bonded to that carbon right there.
Oh, right.
Yeah. Okay. Because when this oxygen minus attacks the aluminum, it creates that new bond right there between them, the oxygen and the aluminum. Okay. So now, did you want to go over the other material on the notes, or did you have any questions or problems that you want to go over, Elysia?
Yeah, was the 4th problem like hard?
Oh, right. Yeah, the 4th problem here. Oh, wait, this one, yes.
It was like the terbutyl group.
Yeah, the terbutyl group with the carboxylic acid. Reducing that with a weak reducing agent, sodium borohydride, will give us no reaction.
Okay.
Right. Because we have a carboxylic acid reacting with a weak reducing agent. Carboxylic acid requires a strong reducing agent, like lithium aluminum hydride, to go through. But if we try to reduce it with a weak reducing agent, like sodium borohydride, nothing's going to happen. No reaction.
Okay. And are there other ones that are considered weak or like common weak?
There are other ones that are considered weak reducing agents, like NaBH3CN, but that is going to be taught in 118C, and you're going to learn about another one in 118B. Oh no, 118B. Yeah, 118B and 118B. So for 118A, just know these two: sodium borohydride and lithium aluminum hydride. Wait, and know which one is the strong one, and know which one is the weak one. The weak one is the sodium borohydride, the strong one is the lithium aluminum hydride. And I know which reactants can react with those, right? The lithium aluminum hydride can reduce everything, right? Because it's a strong reducing agent. It can reduce the aldehyde, ketone, and carboxylic acid. But the weak reducing agent can only reduce the aldehyde and ketone. So this table might help here. I'm going to give you an oxidation table and a reduction table. So for oxidation, there's two oxidizing agents. Do you remember which the strong one and the weak one?
The strong one's Jones.
That's right.
And weak is PCC.
Yes, that's right. Weak is PCC, strong is Jones.
CH2,
Yeah, CH2Cl. The CH2Cl is an A product solvent. So you will most likely see that with PCC at the A product solvent. Right. So if you see these alcohols here and we want to oxidize them with these oxidizing agents, let's think about primary alcohol. What would primary alcohol turn into if we use a weak oxidizing agent, PCC?
We said that it would do an aldehyde, and then the other one was a carboxylic acid, I think.
Yes, that's correct. You got it. Yay. Yay.
Yay.
Yeah. Where the carbon there holding the alcohol is going to be the carbon and carbons of the aldehyde or carboxylic acids right there. Right?
Yeah. And then both of the two below it they're the same, they're ketones.
Yes, same for ketones. You got it. Where the carbon holding the alcohol is going to be the carbon neocarbons of the ketone. Nice. Next one, tertiary.
No reaction.
Yep, no reaction. And why? Why is there no reaction?
Because it has no hydrogens to give.
Yeah, and that was an explanation problem for one of the like OChem professors class. Like why do we see no reaction with the tertiary alcohol trying to do oxidation? Right. Okay, so now that's the oxidation table for reduction. This is what you could. Well, I'll give you the layout, and I want you to predict the products. Okay, so what are the three functional groups that I just drew out?
Aldehyde, the carboxylic is the bottom, and I keep getting ketone.
Ketone, yes, ketone. Ketone. When you see a carbonyl in between two R groups, that's a ketone. And the way that I remember it, it might help, it might not help, is that it looks like a key.
Yeah.
Looks like a key between two R groups. And aldehyde, the way that I remember it is that aldehyde is a hydrogen hiding.
Yeah.
Hiding.
You told me that one 2C.
yeah. In Chem 2C, I remember that. Yeah. In person, right? Oh my gosh. Yeah, Chem 2C gave a good. Do you think it gave you a good foundation for OChem or not really?
Yeah.
That's good.
I think from like what you suggested too, definitely did help.
That's good. Okay, so let's say I give you these reducing agents here. Which one is the weak one? Which one is the strong one?
The weak is Na and lithium is the strong one.
Yes. Now let's look at the aldehyde row. What would the products look like with sodium borohydride?
Well, we know that it can react, but it's like aldehyde is one of the only ones that Na as a weak agent can react to. Lithium can also react.
Yes. Right. So both can react with it. So if both can react with the aldehyde, what product would we get from reducing an aldehyde?
Is it alcohol?
Yes, an alcohol. What kind of alcohol? Primary, secondary, or tertiary?
Is it a primary?
Yeah, primary alcohol, right? Because oh wait, like primary alcohol here, where the carbon holding the alcohol was the carbon to carbon. Because when you see a reducing agent, you think of adding a hydrogen to something, right? A H minus ion, and that H minus ion is going to attack that carbon to carbon, pop the bond onto the oxygen, and that's why this blue carbon here has two hydrogens. Before it had one hydrogen, but now it has two hydrogens from this H minus ion from the reducing agents.
Right.
Right. And then the O minus will just get protonated by the second step to become OH, like that.
Right.
Uh-huh. So now let's think about the ketone. What products would we get from the ketone?
I wanna say it'd be a secondary.
Mm-hmm. Yep. Secondary alcohol for both, because the weak reducing agent and a strong reducing agent can reduce a ketone down into a secondary alcohol, right? Where did the secondary alcohol get its hydrogen from? Because before that, blue carbon did not have a hydrogen.
It was from the water that came in. I mean the H3O plus, sorry.
Yeah, so the H2O plus hydrogen is this H right here, the one I'm boxing, right? Because that is going to become an O minus somewhere in the mechanism, and the O minus grabs that H to become OH, neutral, by the H2O plus. Right.
Mm-hmm.
So,
Was it the the negative charge, like the partial negative?
yeah, the negatively charged hydrogens of the reducing agents. Right. So it would be like if it's BH4, one of these hydrogens here with, or the hydrogens don't have a negative charge directly. It's the boron or aluminum that has a hydrogen, but the hydrogens act like they have a H minus ion, hydride ion. And if it's aluminum hydride, it's going to be one of those four hydrogens, where one of these hydrogens here is going to attack that carbon to carbon, pop the bond onto the oxygen. And when that happens, that gives that blue carbon a hydrogen, which comes from the hydrogen of the reducing agent.
Right.
So the hydrogen here of the secondary alcohol gains a hydrogen, aka reduction, from the reducing agent, right? Because if something is an agent, like reducing agent, it will reduce something else. NABH4 and LiLH4 is a reducing agent because they are agents of reduction. They're going to reduce this ketone here. They're going to have that ketone add a hydrogen to itself.
Right.
Okay. And that does the same thing for this aldehyde as well. We added an extra hydrogen to that blue carbon, which came from the reducing agents. But when we do that, we have to pop the bond onto the oxygen, which becomes O minus, and then the O minus grabs the H from the H3O plus to become OH, neutral. Right. So if I were to highlight where the hydrogens came from, the reducing agent hydrogen makes these hydrogens on where the carbonyl was, and the H3O plus hydrogens is going to be the hydrogen of the OH. Right. Okay. Now let's look at the carboxylic acid row. What products would we get from that?
I wanna say that NaBH4 won't react,
And maybe short, yep. So no reaction. That's right.
but I think lithium aluminum. Did you say is
Hydride.
Hyd-
Hydride. Right.
yeah.
Because whenever you
I
see
think it would
NaBH4 or LiH4, you think of H minus ion, which is hydride.
hydride.
Hydride, right? H minus.
I think it would be able to react.
Yep, it would.
Um, uh, I don't know too what though.
Yeah. If you were to give it a guess, what do you think? What do you think?
Um, a primary?
Yes, primary alcohol. That's right, primary alcohol. Where to predict the product quickly, all you have to do is to just get rid of the carbon double bond oxygen, get rid of that carbonyl, and you get to your right answer right away. the mechanism, we went over it like today and yesterday, but I wouldn't worry too much about it. I don't think it's gonna show up on the exam. The reduction of carboxylic acid, right? It's like this whole thing when we like create this good Debye group simultaneous thing. Like the reason why it's weird is because of this step specifically, right? But I think you understand that step, right? Like
Yeah.
this simultaneous thing. That's good because one of the reactions in 1b, the Bayer-Villiger reaction, is going to have this simultaneous like kind of arrows too.
Okay.
Yes. Yeah. Okay. And we could say that he gained 2 new hydrogens from the reducing agent, sodium borohydride or lithium aluminum hydride, and this hydrogen of the OH came from the acid workup, H3O plus. Okay. So that's reduction and oxidation table that I think about when it comes to alcohols, like these tables here.
Okay, thank you.
No problem. And another thing that might show up, which showed up on Levin's test before, that a lot of people like didn't know, is that if you start with an aldehyde, there is a way to convert that into a carboxylic acid. But do you remember what kind of reagent we would need to use to do that? What kind of oxidizing agent?
Um,
It would be one of these two here, the weak one or the strong one.
wouldn't it be Jones?
Yep, Jones. Right. Yep, because if you use PCC, PCC can only oxidize at max to the aldehyde. So if you have an aldehyde and you try to do PCC, nothing's going to happen because it's already at its most oxidized state from PCC. But if you want to further oxidize it, further add an oxygen atom to it, we have to use the stronger oxidizing agent, Jones.
How would that look like as like
Mechanism.
yeah.
So all the professors does not go over the mechanism for Jones for this. I'm not sure. Like I don't know. We just know that it oxidizes, but I don't know the full mechanism for it.
Right.
And it's
Okay.
never tested. The mechanism for this is never tested. We just have to know what the definition is um, for oxidation and reduction is, and then do it, and then recognize PCC and Jones and what they do to these kind of alcohols. Yeah, but don't worry about the mechanism. But that's a good question though, because looking at the mechanism helps you understand how we transformed one molecule to the other.
Right. And so you were bringing up this situation with aldehyde because if we wanted to further, like if we were given an aldehyde and we want to oxidize it more, right?
Yeah.
Then we'll need it to react with a strong reducing agent or oxidizing agent,
Oxidizing agent, yes.
which would be Jones.
Yes, which would be Jones. And instead of saying Jones, you might see a lot of chromium and a lot of oxygens, which is either that form or you might even see it in this form here, which are forms of Jones reagent. A lot of chromium and a lot of oxygen with acid and water, which represents Jones reagent.
Okay.
Uh-huh.
So in some cases, like for an exam,
Mm-hmm.
do you think that they would write Jones or do you think they would like write like NaCr
Uh-huh.
two?
Yeah. For leave-ins, she does it this way: the Na2RCO3 in helix as well. Nasiri, she like mix it and matches them sometimes. I don't know. She's like unpredictable with these sometimes. But for Wei, she uses Jones only. Like on her lecture slides, I didn't see her using these reagents for Jones. She just put Jones as the reagent.
Okay, yeah, because I was a bit nervous whether or not I was gonna have to memorize it or
Yeah, yeah. But you do have to know it for Helix though. Like you will see this again in Helix class for when it's in BE.
okay, yeah, I
Right.
have Helix.
Yeah. Yeah, but you'll be fine. I think Helix, I don't know, because I don't know how waste exams are. Like, yeah.
Okay, thank you.
Yeah, no problem. Yeah. So the next thing that we can go over is going to be organometallics, the Grignard reagents. Right. Wait, actually, let me go answer Kathy's questions first, and then if we have time at the end, I'll show you the Grignard reagents, and then Kathy's questions might even have Grignard reagents in them, and then if they do have them, then I'll go over it when I go over those questions. Right. Okay. Yep. So Kathy, you want us to go over 3, 4, 5, 6, 7, and 8 on the problems that you sent me. Let me download them. Okay. Notability. Add to note. Import. Open. Okay. Let me share screen. Okay. Oh, not this one. This one. Okay. So you wanted to go over 3, 4, 5, 6, 7, and 8. Oh yeah. So this is perfect. I didn't even know that those Grignard in here. Grignard 8. I just had a feeling that one of the questions that Kathy asked is going to be talking about organometallics, and then like the alcohol chapter. And this is exactly it. The organometallic thing. That was good. Good. That was good. Okay. Okay. So before we go over those problems, let me just explain the organometallic stuff with alcohols. So organometallic reagents is an umbrella term, right? Because there's multiple organometallic reagents. The most common one that you come across is a Grignard reagent. The other form that you may occasionally see, but not as much as Grignard reagents, is going to be organolithiums. But they're going to do the exact same thing. They're just represented differently. And a Grignard reagent is going to be R, Mg, X, where X is a halogen like chlorine or bromine. But in most cases, you're going to see it as bromine, right? The most common one is bromine. So you're going to see it as like RMgBr, which is what I'm going to be using for this when I teach this. But you could also see MgCl, which some professors use sometimes. But most cases, you see MgBr. Organolithium is just going to be R-Li, R-lithium. So some examples would look something like this. Right? Where you have an R group, which is any random hydrocarbon group attached to an MgBr or a lithium, right, for the organolithium. But they're going to do the exact same thing. So look at the first carbon attached to the Mg, magnesium, or lithium, which is going to be these stars here that I'm going to star. Those starred carbons there that is directly attached to the magnesium or lithium is going to be negatively charged. And if an atom is negatively charged, would that be nucleophilic or electrophilic? Nucleophilic. Yes. So these carbons here are going to be the nucleophiles. Right. And these nucleophiles here can attack things like electrophiles. But these starred carbons here are not only nucleophiles, they are also bases. So if you put some kind of acid to it, then you're going to protonate that nucleophile, that base, right? So I'm going to give you examples here where let's say we have this Grignard reagent. What is the charge of this carbon here directly attached to the magnesium? The first carbon directly attached to the magnesium. So it is neutral charge, but what would be the partial charge if it's directly attached to magnesium? Negative charge, right? And the way that you could think about it is that think of carbon as being more electronegative than the magnesium or lithium, right? Carbon is more electronegative than the carbon and lithium, making that carbon partial negative charge, right? So this carbon here will have the partial negative charge here. So that partial negative charge can act as a nucleophile or a base. And I'm going to show you different things that it could react with. Let's say 4 things. Okay. First step, that. Second step, acid workup. First step, this. Second step, acid workup. Let's do that. And let's just do acid workup here. So I'm going to label these reactions 1, 2, 3, and 4. Okay, so I'm going to look at reaction 1 first. Right, reaction 1, which is going to have this organometallic, this grignard reagent to be specific, reacting with this aldehyde as the first step, in the first step. And the second step, we have acid workup. So when you see a step-by-step process like this on the arrow, only focus on the first reaction first and ignore every other reaction like 2, 3, 4, 5, or 6, because this first reaction here is just going to react with the reactant molecule, and then the product of that first reaction is going to be the reactant for the second reaction. So after we get the product of this first reaction here, let's say that's product P, that product P is going to react with H3O plus in the second step to create the final answer. Right, so for now, let's ignore the acid and let's focus on this aldehyde here. What partial charges do you see on this aldehyde and on what atoms? Partial negative on oxygen, that's one of them. Nice. There's one more partial charge. Partial positive on the carbon, right? Which carbon though? This left carbon here is going to be neutral because it is attached to 3 hydrogens, 1, 2, 3, and 1 carbon. The difference in electronegativity between these 2 carbons here is 0. So there's no partial charge there. The difference in electronegativity between the carbon and hydrogen is like 0 point something, very, very small, very negligible. So there won't be any partial charges on this carbon here to the left. Right? Does that make sense on like why there's going to be no partial charge on this left carbon? Yeah, but if you look at the right carbon right here, this one, the carbonyl carbon, it's attached to an electronegative oxygen atom, right? The difference in electronegativity between this oxygen and carbon is big enough to have a partial positive charge on that carbonyl carbon, right? A carbonyl, whenever I say carbonyl, that is going to mean a carbon double bond oxygen. So a carbonyl is a carbon double bond oxygen. But there's a lot of carbonyls. There's aldehyde, ketone, carboxylic acid, ester, amide, anhydride, isohalide. Carbonyl is just a umbrella term, like all carbon double bond oxygens. So this is the carbonyl here. So this carbonyl carbon is that carbonyl carbon. This is the carbonyl oxygen, right? So these are just terms that you have to be familiar with, because they might talk about it in test, or your professor might talk about it when they teach the material, right? So this carbonyl carbon here is going to be partial positive charge because it's attached to this electronegative oxygen atom. Right? Does that make sense? Yes. Okay. So now I'm going to dot this electrophile right here to show that that's my electrophile. So in organic chemistry, do nucleophiles attack electrophiles or do electrophiles attack nucleophiles? Nucleophile attacks, right? So we have our nucleophile here, which is this star, this partial negative carbon. I'm going to have that starred carbon attack that dot carbon, the electrophile. And then whenever a nucleophile attacks an electrophile, they're trying to make a new bond. So we're trying to make a new bond between the star and dot, between the nucleophile and electrophile. But that's going to be problematic for this dot carbon, because when we try to make a new bond right there, that's going to break the octet rule. Do you know how we could like conserve the octet rule after we do that attack? Like what can we kick out? What can we pop up? Take the double bond onto the oxygen. Yes. Pop this double bond onto the oxygen, right? Those 2 electrons on one of these bonds are going to go into the oxygen to give that oxygen a negative charge. And as this reaction occurs, the MgBr will dissolve in the solution. It's just going to go bye-bye. It's just going to disappear, right? So a lot of students, when they learn this reaction, this is where they mess it up. Like, we have to connect these 2 pieces together now. We have to connect the nucleophile and the electrophile together. And a lot of students, they add an extra carbon by accident. They lose a carbon by accident, or even if they have the right number of carbons, they put the wrong groups on the wrong carbons. So the reason why I starred the nucleophile and dot the electrophile is because it helps me keep track of my carbon and the groups on the carbons, right? So what I mean by that is, let me draw out the starred carbon like this. This is the starred carbon, which is attached to this cyclopentyl group here, right? And it was attached to the MgBr, but we said that when this reaction occurs, the MgBr goes bye-bye. It just dissolves into ions. So it's no longer there. When this star here attacks that dot, we're going to make a new bond between the star and dot like that. So this is the new bond that we formed from this reaction, the new bond between the star and dot. Okay, so now we have to see what is attached to this dot carbon. The dot carbon here is attached to a methyl group, and I'm going to draw that methyl group like this. It doesn't matter where you put it. It could go up like here, or it could go down here. It doesn't matter. Same thing. It's attached to a hydrogen, but I'm going to leave that hydrogen as invisible, right? It's somewhere here, but it's going to be implied. And it was double bonded to an oxygen, right? This dot carbon was double bonded to an oxygen, but now it's single bonded to an O minus because we popped that double bond onto the oxygen right there to create this O minus right here. Now, once we have that, that's the end of the first step, right? That's the end of the first step when we react this Grignard reagent with this aldehyde. Now, when we bring in the second step, what do you think the second step is gonna be? But before that, did that make sense? Like how we got to this end of first step product? That's good. So once we get to that end of first step product, let's bring in the acid. What do you think the acid is gonna do with the product of the first step? Yep, the negative charge on the oxygen is going to grab one of the hydrogens of the acid, kick out the conjugate base, and make the O minus into an alcohol to make it neutral. Like that. Final answer. Yeah, will attack or grab the hydrogen. Yes. When I do nucleophile electrophile, I say attack. When I do acid-base reactions, I say grab. Right? It's just like how I say. You might even say deprotonate, protonate, right? This O minus here is deprotonating this acid. Another way you could see it is that this acid here is protonating this O minus. If that makes sense. Like this O minus here is getting protonated. This H3O plus here is getting deprotonated. And the proton is a hydrogen, acidic hydrogen. So the first step is nucleophile electrophile, and the second step is acid base. Yes, it is like so. First step is nucleophile electrophile. Second step is acid base, like SN1, right? But the SN1 first step is not nucleophile electrophile. That like the end of SN1, right? Because the very first step of SN1 is the leaving group leaving, right? So it's similar to SN1's last steps, right? Yeah, the first step here, nucleophile attack electrophile, pop the bond onto oxygen. Once we get that product, then we do acid base to neutralize that O minus to get this final product here. Right. And whenever we do organometallic reagents or reactions, we're always adding carbon-carbon bonds, right? Organometallic Grignard reagents or organometallic reagents is always adding new carbon-carbon bonds. So in synthesis, when you see new carbon-carbon bonds, you know that you're going to do an organometallic reagent, right? Before, this is our original reactant molecule here, and this is our final product here. This is the new carbon-carbon bond that we formed right here, right? Because that carbon-carbon bond was not there before. And this is also the new alcohol because the alcohol came from this aldehyde here that we used. And then once you guys are familiar with that, and you guys start learning about synthesis problems, I'll show you guys tips and tricks on retrosynthesis, on how to go backwards and how to find what bond to cut and disconnect to predict the previous reaction, the previous reactants. But for now, let's focus on the forward reaction, which is this right here. Okay. Now, if we look at the second reaction, it's going to be very similar to the first reaction that we just did. So let's say we have the same Grignard reagent, this R, MgBr, but our second reaction is going to be this right here. So what do you think is going to happen in this reaction? Right, how would you think about this reaction? Yeah, partial negative charge on the carbon directly attached to the magnesium, which I'm going to star because I always star my nucleophile. You could add any other shape, or you could like number it if you want, but I like starring my nucleophile atom, the partial negative atom or the full negative atom, right? Attacks the carbonyl carbon, which is partial positive. That's correct. And what else is going to happen when after we attack the carbonyl carbon here? Because a octet row is going to be broken here. Kicks out the double bond onto the oxygen. That's correct. And once we do that, we're going to get, and what happens to the MgBr? Like, does the MgBr stay or does it go away? It dissolves. Yes, it dissolves. It would go away. It goes bye-bye. And when we make a new bond between the star and dot right there, what is attached to the dot? The electrophilic carbon, the dot. Methyl and O minus. So there's no H here, right? This dot here has no H's, right? Let me make it different by changing this right here. So let's say we have that and this. Okay, yeah. So before it was two methyls, but now I changed it. There's one methyl, one ethyl, right? And because there's one methyl, one ethyl, I'm going to draw it out like this. And there, you could draw it like any order, any orientation you want, but I'm going to draw out my methyl out like this and my ethyl out like that. Does that make sense so far? You could have switched that as well. You could have drawn the methyl here and the ethyl here, but I'm drawing it out like that, right? And it's also bonded to a single bond O with what charge now? When we pop this double bond onto the oxygen, a negative charge, yes. So that's the end of the first reaction. The second reaction, H2O plus, what kind of reaction would that do? O grabs H, yep, and then kick out the conjugate base, protonate the O minus, neutralize it to give us our neutral alcohol here, like that. Does that make sense on how we got to that final product? Yes, okay. So now let's move on to the third reaction of this organometallic here. So when we have this organometallic, MgBr, and let's say we react it with this right here, just this. Okay, now how would you go about this reaction here? Think about the properties of the organometallic, what charge they have, and the properties of the reagent, what charge they have. What is that? And what are they going to do to each other? Yep, C on MgBr attacks C attached to Br. That's correct. The C on MgBr is the nucleophile, the star, because it's partial negative charge. The C attached to the Br is the dot, the electrophile, because it's partial positive charge. The star is going to attack the dot. And what other error happens when the star attacks the dot? Right, when the nucleophile attacks the electrophile? there's one more arrow that's going to happen here, right? To conserve the octet rule. Yep, kick out the Br. The bond between the electrophile, the dot, and the Br, those two electrons are going to leave and kick out the bromine, right? Go onto the bromine. And this is an SN2 reaction, right? Where the nucleophile is the grignard reagent, the RMGBr, and the electrophile is the haloalkane, the alkyl halide. And as a result, we are going to get this product here, where the MGBr dissolves. That's the star. This is the new bond between the star and the dot. And what is attached to the dot? What is attached to this dot? Yep, an ethyl group. The bromine group is no longer there, right? It was attached to the dot, but we kicked that out when we did the reaction. So now in the product, this dot is only attached to an ethyl group, which is this ethyl group here. And that's the final answer there. Okay, did that make sense? Yeah. Okay, now let's move on to the last reaction here for organometallic. Let's say we have the same organometallic. Instead of saying MGBr, you could say Li as well, but it's the same thing. Whatever is attached to the Li is the star, the negative charge. But now let's react it with H2O+. What will H2O+ do to this nucleophile base? And then it might give you a hint if I draw out the H2O+ like this. So the O is the one that has a positive charge, but this star here is not going to attack the O, because when we make a new bond between that carbon and oxygen, we can't kick out any H's. All these H's here are very bad leaving groups. They're the worst leaving groups ever. So this is a strong acid. So that's strong. So yeah, it's going to grab an H. This star is going to act as a base, grab one of the H's, and the bond between the H being grabbed and that oxygen is going to break and go onto the oxygen right there. And that's going to give that star carbon a hydrogen and dissolve the MGBr. So this is the final product here, where the hydrogen is grabbed. I'm just leaving that as implied. Well, actually, let me just draw it out to make it more clear. But in the answer or the test or the mechanism, you might see it as implied, right? Where if I highlight this hydrogen in yellow, right here, that hydrogen being grabbed is that hydrogen right there. But you could have left it as invisible or implied. Did that make sense? The positive charge at the O. So how many pairs of electrons does this oxygen have with the positive charge? One pair, right? And when we kick that out, we are going to have this right here, where this oxygen here gains a pair of electrons from that bond. So this oxygen here now has two pairs of electrons. And what is the formal charge of that oxygen with two pairs of electrons and two bonds? 0, right? So it's neutral. And then this is also known as H2O, water. If this was a predicted product problem, you don't have to include this because this is inorganic. There's no carbon hydrogens here. There's no hydrocarbons. So that's why you didn't have to include that conjugate base of this acid. That's the conjugate base of the acid. But if this was a mechanism problem and they wanted you to draw the other mechanisms, they want you to draw all the leaving groups, all the conjugate bases, all the inorganic molecules as well. But if this was predicted product, they just want the major organic product. Yeah. Okay. So let's end off office hours by answering this question 3 right here. And I want you to describe what do you think is going to happen here. Oh, I forgot to teach one thing. So the organometallic, right? The MGBr, our MGBr, how did we get that in the first place? So if we have any halo alkane like this, and we want to convert that halo alkane into a grignard reagent MGBr, we just have to put magnesium in ether, right? Magnesium in ether, where ether is the A product solvent. That's not going to do anything in the mechanism. It's just there chilling, allowing the reaction to occur. But this magnesium here is going to insert itself between this carbon and that bromine right there, which is going to give us this Grignard reagent here. Does that make sense so far? Like that's the whole thing. That's the whole mechanism. When you see Mg and halocane, it's just going to put itself in between that carbon and bromine right there. And that does something very interesting, right? What is the partial charge of this carbon right here that is directly attached to the bromine? Positive. What about this carbon right here that is directly attached to the magnesium? Negative, yes. So we changed the polarity of that carbon right there. Before it was positively charged, now it is negatively charged because we turned this electrophile into this nucleophile by converting this halocane into this Grignard reagent. And all we had to do was put magnesium in ether to do that. Okay, did that make sense? Yeah, and then from this Grignard reagent here, you could all do any of these 4 reactions here that we just went over. Okay, so now you can do a 3. Now you can do a 3. Explain how you would do a 3 here. Okay, yep. First step, creates the MGBR. Magnesium inserts itself between that carbon and bromine to create MGBR. That's the end of the first step. Then this C attached to the carbon is negatively charged, the star. That's my star atom. Yep, the alpha carbon. You could call it the alpha carbon with the first carbon attached to the magnesium. Okay, yep. What would that do to the second step? Let me draw out the second step for you, which is this benzene attached to this aldehyde. Attacks C attached to the O, yep. Attacks the carbonyl carbon, which is the dot, the partial positive carbon. And what else happens? And the oxygen gains a pair of electrons, right? Get rid of the double bond. The double bond pushes onto the oxygen or pops onto the oxygen. Now, this is the step where most students mess up on, connecting those 2 pieces together. But the way I do it is I star the nucleophile, dot the electrophile. And what happens to this MGBR? When I draw out the next thing, it dissolves. It just goes bye-bye. Right? Dissolves into ions. This is the star. This is the new bond between the star and the dot. Now, what is attached to this dot? O minus and H. Before it was double bonded to O, but now it's a single bond O minus and H. So I'm going to draw that single bond O minus down here. The H, I'm going to leave that as implied, invisible on this dot carbon. It's right here, let's say, but it's going to be invisible. And there's one more thing that this dot carbon is attached to. And the ring, yes, the benzene ring here. Nice. Now, that's the end of the second step. Now let's bring in the third step reagent. What would this third step reagent do to the product of the second step? Yep, negative O attacks the H. There's one more arrow as well. The bond between the hydrogen being grabbed and the oxygen is going to break and go onto the oxygen right there. Goes onto the oxygen, yep, to create the conjugate base. And that will give us our final answer here. And if you wanted to draw out the side product, it would be water, the conjugate base of the H2O plus acid. So looking at the answer choices, that should be B. Right. Let me copy and paste this so we can compare. Like that. Okay. Does this make sense? These two here are the same thing. Yep. Okay. Did that make sense for you too, Elysia? The organometallic Grignard reagents?
I think I don't get the last part.
The last part, like the acid workup step with the H3O plus.
Yeah.
Yeah. So do you get to this part right here where we get the new bond and the O minus?
Um, I think so.
Yeah.
Yeah.
So once we get to this point right here, the last step's job is to make this O minus neutral, right? And to make it neutral, we have to protonate it. And the last step here is an acid, H2O plus. So the last step here is an acid-base reaction. Our base is this O minus. Our acid is this H2O plus. So this base here, the oxygen minus, there's 3 pairs of electrons on that oxygen. One of the pairs of electrons on the oxygen is going to attack or grab this H right here. Like it's going to grab that H, rip that H off of this rest of the group there. And the bond between that H being grabbed and this oxygen here is going to go on to the oxygen. Those 2 electrons there of that bond is going to go on to the oxygen, which gives us our water molecule, right? And then this H here that is on the oxygen is, if I highlight it in yellow, that H there is this H here being grabbed.
Right, because it's an acid.
Yeah, this is an acid, right? And this is the base, making this an acid-base reaction.
Yeah.
Right. Yeah, but the rest of the previous steps make sense, right? Like how we got to this point here.
You were saying that we have the MGBR dissolve and then we have to put them together.
Yeah, because the carbon directly attached to the MGBR is the negative charge carbon, the nucleophile.
Right.
The carbonyl carbon is the partial positive electrophile. And in organic chemistry, nucleophiles attack electrophiles. So this starred carbon here, the carbon directly attached to the MGBR, is going to attack this carbonyl carbon. Does that arrow make sense? Like that specific one arrow, when this star
Yeah,
attacks
so
the dot?
one bonds to that one, which is our new bond.
Yep, that's the new bond. This new bond right here that we make between them. And the MGBR dissolves away as a result. But when that happens, that's going to be problematic for this dot carbon because it's going to have 5 bonds when we try to make a new bond there.
That's why
Right.
we have as a negative, and then we satisfy it by the floating H3O plus, and that's our acid base reaction. So
Yes.
then it becomes an OH and it's happy.
Yeah. Yeah, you got it.
Oh, okay, that makes sense.
Yeah.
So you said electrophiles attack nucleophiles.
Other way around. Other way around.
Nucleophiles attack.
Electrophiles. Yes.
Yeah. Okay.
Yeah. And what charge do nucleophiles have?
Negative.
Negative, right. And what charges do electrophiles have?
Positive, because
Positive, right. And the reason why that is because the things that move are the electrons. Electrons are the ones that are moving towards the positive charges, the ones that are missing electrons, an empty void, you could say.
Okay, yeah.
Of electrons, right? Because the nucleophile has
go to electrophiles.
Yeah, nucleophiles goes to electrophiles. Yes, nucleophiles goes to electrophiles. Nucleophiles attacks electrophiles.
Okay.
Yep.
Okay, that makes sense. Thank you.
Yep, no problem. Okay. Do you guys have any plans for Thanksgiving break tomorrow or Thanksgiving Day tomorrow?
I think I won't really be doing anything like in particularly throughout the the morning and afternoon, but I'll probably eat dinner later because my grandma, she likes to cook for Thanksgiving.
Oh yeah, turkey or any other?
Well, so it varies. Sometimes she likes to make Filipino food, and then other makes like flan, shepherd's pie, like
Oh, are you Filipino, Alicia?
yeah.
Oh, I see. Yeah.
Good.
Yeah. What is that, Joseph? Filipino chicken? Jollibee?
Jollibee.
Jollibee? Okay. Yeah, it
How
was
about,
nice. Yep.
how about you?
Oh, me? Tomorrow, my family isn't doing a family party tomorrow. We're doing it on Saturday, so probably just rest. Not sure what I have planned tomorrow yet. Office hours, of course, 9 to 10, because I have nothing planned tomorrow yet. Um, and then family Thanksgiving party on Saturday this weekend.
Ooh, fun.
Yes.
Thank you so much,
Yeah.
Brian.
No problem, Alicia. See you guys. Good night.
Good night.
Bye.